and I am a PhD candidate at Vanderbilt University. I study galaxy evolution, and I will be defending in June, so I'll be a real life doctor soon. Um, and I am a PhD candidate at Vanderbilt. And go ahead, Jess.
Oh, hi everyone. My name's Jess. I'm also a PhD candidate at Vanderbilt. We are here today to talk to you about some astronomy. Liv and I run a non-profit together, which has been providing science communication for the whole convention so far. We've also been doing a bunch all around the country, thanks to lovely Ryan, who's here with us somewhere in the quietness of the room. But yeah, today we're going to talk to you. I'm gonna share some slides and hopefully have a good time talking about some science. Liv is going to check the YouTube and deal with the comments there. So if anyone has any questions at all, feel free to put them in there and we will answer them. I'm going to
We
share.
also have a little bit of like audience participation, so get ready to answer some questions.
I will be very mindful with audience participation. I know what virtual conventions, virtual conferences are like. We've all been through a lot of them, as Liv has as well, doing astronomy in did we say we're astrophysicists, Liv? I didn't think we did. You did.
No, well, I said I was a PhD candidate studying galaxy evolution, but yeah, we're astrophysicists. We run a nonprofit called the Neuroverse Initiative, which I'm sure you're seeing a lot of as we are doing or providing the science communication for this awesome online virtual con. And our nonprofit deals with neurodiversity and space sciences. And if you couldn't tell already, we are both very neurodiverse. You'll learn more about that as we go on. So yeah, science.
Okay, yeah. So let's talk today. We're gonna do two talks with you today. The second one is in a few hours. I'm sure Liv will text me and tell me what time it is for the millionth time because I always forget. But right now, we're going to talk a bit about the Kardashev scale, the prime directive, and habitable exoplanets. A lot of the talks that we're giving this week, and this one specifically, links back to Star Trek. So we both are big Star Trek fans, as a lot of astronomers are. And today, what I really want to do is see if we can persuade y'all. I shouldn't say y'all, should I? It's too distracting in my accent. We're going to try and persuade you guys that we are on the Star Trek timeline. And if this logo wasn't enough, I feel like this logo is more politicized in this talk now, and we probably shouldn't do it. But anyway, here we are, living the dream.
How many of you actually think that we are on the Star Trek timeline? I can see.
Oh, we're doing. Oh, I love this for you, Liv.
Yeah.
I can't see them.
Ooh.
It's like a surprise.
Nothing yet.
Why
All
don't
right.
you shout out as we go along?
Yeah,
Okay,
I'll
so
keep it going.
okay, so we're going to answer three questions today. These questions are, if aliens exist, why have they not made contact? Do aliens exist to begin with? And where are they? So these are three questions that I generally get when I'm reading the chat. Thank you, Ryan, for putting comments in the chat to distract me. I love it.
Don't do that.
Don't look at the chat, Jeff. So these are questions that I often get when I go into schools or we go to conventions and we talk about what we do. Liv has mentioned that she works on galaxy formation. I work in galactic archaeology. So this is an area of stellar astrophysics where we use the stars to determine the formation and evolution history of our galaxy. And with that comes a lot of questions about how we got here. That is the ultimate question. And I think that's the question a lot of people have. And when it comes to determining whether or not we're on the Star Trek timeline, we want to know whether all our buddies that are going to be out there eventually with us in the Federation are actually existing out there right now. So let's start with.
Yes. Would you want to make contact with us? Is exactly what we're going to talk about.
Yeah, exactly. That's exactly what we're going to talk about. So we're going to start with this one. This is usually an audience participation question. We'll see if anyone gets back to us. But these two pictures are of two men that have a lot in common. Actually, they have one thing in common. Does anyone know what it is?
Okay. There's a 20-second delay, so I will read the answers when you actually put them up. Yeah. Go ahead.
Okay, right. That's what we're going to do. So If anyone said it, I'm very excited. And if we were live, we would have prizes. I'm sorry. Do take this as a moment to remember that you should definitely come to all of the Creation Star Trek cons where you'll find us. And usually we're throwing things at you, but they're fun things. And I have a Tribble with me right now. We don't have Tribbles, but maybe we should. Okay. So the combination of these two guys is the last name Kardashev. So the guy on the left, Latisse Kardashev, was in Discovery. This was a really cool episode because it was a nod to Nikolai Kardashev on the right, who was the maker or the maker of the scale. He was the theoretician who came up with the Kardashev scale, named after him. And he was a radio astronomer. They're always a bit odd, in my opinion, but they love a good alien. They are the alien people. And he thought a lot about what it means to find aliens and why they're not communicating with us. So the Kardashev scale looks a little bit like this. This is a simplified version. In fact, the fourth stage was added later on, but the first three stages are from Nikolai himself. He basically thought of this scale as it's essentially an energy scale. So what each of these types say is how much energy a civilization is producing and how much it can not just produce, but how much it can collect and use to power its civilization. So type 1 and type 1 civilization, we're going to go through these, is, I'm going to turn this lamp off because it's really bright. There we go. Okay, so type 1 civilization is an interplanetary civilization. These planets or these civilizations can collect and maintain enough energy that they are able to move from planet to planet. They can wander around the solar system. They can control natural events, things like earthquakes and volcanic eruptions, and they can access all of the energy available on the planet, right? So they can take energy from tectonic plates, things like that, and they can take energy from the sun, but not the whole sun, just the luminosity that hits us, the flux that hits us on Earth. So that's a type 1 planet or a type 1 civilization. A type 2 civilization is interstellar. And these civilizations are able to take the energy from their entire sun and use it, consume it, to run their civilization essentially, and they have the ability to travel interstellar, so to go from star to star. This is where we would see the beginning of the Federation. Well, not the beginning. This isn't a picture of the this is a picture of the TNG Enterprise, but basically this is the kind of civilization we would expect that our level of Federation originated in. I will ask a question now before I finish this slide in case anyone's interested. So on the top right here, this kind of weird looking ball is a real scientific discovery, or essentially an artistic representation of what could have been a real scientific discovery. Does anyone know the name of this discovery? I'm going to leave that and talk a bit about what it represents. But if anyone knows the name of the star, I'll be really impressed. So this was a star that was observed. I want to say this whole thing happened about 6 years ago now, but then it could have been 20. The time in the last 5-6 years is all melded into one. This star was observed to have what looked like a lot of debris around it. And we can't observe that star directly in the sense that we can't resolve what's floating around it. We can't see what's floating around it, but we can infer that from how much light we're receiving from the star. So sometimes when we receive light from the star over time, it'll have little dips in it. And this looks like something's moving in front of the star. Usually this is a planet. So usually this is how we detect planets. And in this case, this was a telescope we were using to detect planets. But for this particular star, it didn't look like a planet crossing at all. It looked like a load of debris. And for a while, people were thinking it might be what's called a Dyson sphere, which is a collection of a man-made structure, essentially, which will allow you to consume and kind of ping back to Earth all the energy from that sun and use it to power your civilization. So this could have been an example of a type 2 civilization, but it ended up being dust, I think. Liv, did anyone guess what it's called?
Not that I can see.
All right.
Scotty, it was one of the answers. Boston.
It was Tabby's star. All right, let's do three. Okay. Civ 3. Not the video game. Oh. Okay. Civilization number 3 can move intergalactically. A good example of this from Star Trek is Species 10C from Discovery. They were the first outside of our galaxy, or at least, no, okay, this was the first time that we traveled outside our galaxy in the Federation to visit Species 10C. I know Liv likes telling the story of them. Do you want to tell the story of Species 10C, Liv?
Well, I mean, I want to tell the story of this rock, which is geologists don't at me. Does anybody know the name of this mineral anywhere? It's actually a real life mineral. We have it on Earth, and it does the same thing here that it did in Star Trek. So if you get this one, it's super cool. But
is that true? I didn't know that. Oh, well, of course it does. Never mind.
Of course it does, because Star Trek's awesome. But it's called boronite for anybody who doesn't know. And it is one of the prettiest minerals that I've ever seen, but it also acts as like a soil fertilizer. And also, I read Boston before. It says boson, as I was told in my own chat box. So I can read, I promise. Yes, anyway. Boronite, super pretty soil fertilizer, which means you can use it in terraforming planets or areas of ground that are not currently able to grow stuff.
Sorry, Liv.
Good.
No. I want to hear more about boronite. I love. Is this one colorized or is this a photograph?
This is a photograph. This is an actual photograph of the real one.
Can we get some boronite for Las Vegas? Again, big shout out, guys. Come and visit us in person in Las Vegas. Can we get some boronite? Is it expensive?
I don't know. We share a geology floor, so
I am not a geologist. I'm like, let's get some rocks. Let's do it.
I can go ask them. I don't.
Let's go out. Okay, we're gonna go ask the geology department. The rock people. They're really fun, I think. Okay. So, are there any good rocks in Nashville? We're at Vanderbilt, by the way. I live in Hawaii. There's good rocks here. Liv, are there any good rocks in Nashville?
There's lots of roads that have cutouts of sediment, so you can see sediment layers as you're driving down the highway, which I always thought was cool. But
that's
like
really cool.
Stuff like this, I'm not that I know of, like off the sides of the roads or anything.
Okay. So anyway, thank you for that segue. These types of civilizations can control the energy of their galaxy. They're usually well, you would think of it as a Dyson sphere around the central black hole as opposed to the star, right? You're one order of magnitude, well, not one order of magnitude, many orders of magnitude bigger. There are real numbers for this. They're just not on here because I didn't want to number people with numbers. Okay, type 4. Inter-universe civilization would have enough access to energy to be able to hop around the universes. In Star Trek, Q is kind of the Q continuum is a representation of this, or it could be. There is actually way more discussion about this online than I want to get into, which is why I'm not going to say conclusively what type of civilization Q and his buddies fall into, because I don't want to get shouted at by the internet. But I have also included fart for Rick and Morty fans. Definitely a type 4 civilization is fart. Love a good fart. Okay, so those are the 4 types of civilization. And the question that we're trying to answer here is why, if there are aliens out there, why have they not come to visit us, right? And this links to Star Trek through one of the first general order of Star Trek, which is the Prime Directive, which states no starship may interfere with the normal development of any alien life or society, which argues that until a civilization has reached a certain level, you can't go and talk to them because they're not ready, right? That you would interfere with their development. And this obviously gets definitely followed all of the time.
Never, ever.
Never, ever. Not in like every single episode do they debate this. But I feel like a real life federation would take it a bit more seriously, I would hope. So the level that one has to be at to get their Hogwarts letter from the Federation, wouldn't be called that, obviously, is warp signature. So I don't know if anyone kind of can say this in the chat or anything. This is slowing me down because of the video. I'm going to move on. I'm going to pause this. Oh, it's type 2. I was going to ask this question, but I wanted to slow that video down because my Wi-Fi in the islands is pretty bad. So in order to have a warp signature, you need to be a type 2 civilization because you need to be able to harness enough energy to be able to create that kind of engine. And I'm not going to get into that. That should be another talk, though. We should do like a build a warp engine. What's Liv? Do you know? Do you remember what level we're at? I always do this bit of the talk, so I want to see if you're listening.
Point. Are we asking or are we?
I'm asking you, unless anyone's put it in the comments. I'm asking you, what level do you think Earth and our civilization is at?
We're currently at 0.73, right? 0.78.
Oh yeah, I was going to say 0.72. Yes, 0.73. This is the most, people do research this. This is the most up-to-date, peer-reviewed number. And I should have put a site here. I didn't. I have no idea. Maybe it was, I think it was Carl Sagan actually, because he definitely added the letters. So there was a number of letters added to these levels by, I think it was Sagan, that represent the level of information. So the Kardashev scale represents the level of energy a civilization has. The letters represent the technological advancement. And we're R, which I can't remember the order. I don't think it's alphabetical. But essentially, this means we're in technological adolescence. And this is obviously nowhere close to 2. So the answer for our question of whether these aliens would have contacted us is if they have the prime directive and they stick to it, then no, because we are not ready in the slightest. And what's really interesting about this particular time in the scale is that we are at this very unique turning point where we could either jump to 1 and start to be able to use all the energy on Earth as it should be used appropriately and renewably, or we can self-destruct. And I know every generation says this, don't they? They say we're living in this like unprecedented time, but in this sense, we truly are. So this is just something to sit quietly and think about. Where do we want to go? What do we want to do?
Do we actually want to self-destruct?
Do we actually want to self-destruct because we're heading there? Next slide. Loading quick enough for my...
Everything's fine.
Yay! We're not ready. Okay. Go for it, Liv.
Okay, so the other part about being contacted, right, is that everything in the universe is really, really, really far away from us. The closest star to us is 4 light years away, meaning that it takes light 4 years to travel from that star to us, and we cannot travel at the speed of light, not even anywhere close to the speed of light. So it's going to take a long time. And for things that are even further away, things that are outside of our galaxy, for example, you're not going to be able to see us as we are currently. You're going to see us for however many light years you are away. And so let's say it's 65 million years ago, or you're 65 million light years away. When you look at us, you're not going to see us. You're going to see dinosaurs. And you also have to be on the right side of the galaxy, because since the dinosaurs have departed us, we have actually rotated about 180 degrees. So where we are now is not where we would have been 65 million years ago. So if you're going to see something in this exact spot, you'd see nothing. Or if you were on the other side and still looking at us, then you would see these guys. And Jess likes to give me a lot of crap for this particular slide that we have made, because I apparently made it so that was the where we were and where all these little suns are incredibly accurate, but I didn't let her use dinosaurs with feathers.
Accurate dinosaurs. Or even the right color.
These are cute.
Orange iguanodon. But these are, I will say this, I am very impressed with Liv. She did make me rotate all the Milky Ways to exactly where they should be at the time of those particular dinosaurs. But then for some reason we have these like cutesy, I like them. I'm just saying that if we're going to be accurate, we should be accurate throughout, right? One day I'm eventually going to put real dinosaurs, not real dinosaurs, but real dinosaur images or You know what I mean.
But then you
Okay.
wouldn't be able to make fun of me for this in the future.
Do aliens exist?
In the chat, do aliens exist? How many
It's
of you
gonna
think
okay,
yes?
so I do have a couple of videos in these slides that I'm gonna try and pause or not do because it slows down my video. Um, okay, so we're just gonna move past that. Do aliens exist is a question that we get a lot. And I'm here to persuade you that yes. So these are 3 planets that everyone should recognize, I hope. Or we need to, if everyone saw Rika's talk yesterday, I think she does a bit of planets. Does she do a bit of planets, Liv?
She talks about Jupiter and Uranus and does mention exactly, she talks about where we are in the neighborhood of the universe, which is cool, but not specifically these planets, no.
Well, these are the other ones, all right? So we've got Venus, Earth, and Mars, kind of to scale. Excuse me. And these are the only 3 planets in the galaxy where we have sent robots or where robots live. And let's explore like whether they have life on them, right? So let's start with Earth, because that's a nice obvious one. Earth has life. We know that Earth has life. My coffee order just appeared, and they're gonna come and fill up my coffee. Oh, a different mug and everything. We know that robots exist on Earth, and we know that life exists on Earth. So that's 1 out of 3. Next one is Mars. So there's a rover on Mars. We have seen a rover on Mars. We have sent a rover to Mars even. We've sent many rovers to Mars. And this particular discovery was found about, it must have been, because it was when I made these slides, so it must have been about like 6 to 8 months ago now, of water on Mars. Yeah. So something's happening.
The story though.
Yeah. Can you tell the story, Liv? Because something's happening in this room that distracts me.
Yes. So we completely by accident found evidence of water on Mars. And we did so by this rover was just moseying along and ran over a particularly unstable section of ground. And when they ran over this piece of ground, the ground cracked open. And in it, we found solidified sulfur. And the way in which this sulfur exists in this form on this planet and where it was is the only way that it could have been, the only way that it could have existed like this is if liquid water were once present.
Yeah, thank you for that, Liv. So, and this was the InSight lander, which is a very cool lander because it is a like a seismometer. And some of what I do is look at star quakes. So look at seismology on stars. So I love a good size monitor, but that's not actually what this thing was meant to be doing. So anyway, where there's water, there's very often life. Here's a nice picture of a tardigrade. We all love them. So let's imagine at some
point, from Discovery.
The tardigrade from Discovery, which that's sad. I want that little guy as a pet, little guy. So anyway, hope he's okay.
I was not little.
Well, it's all relative, isn't it? Maybe we all get shrunk at some point. So that's Mars. Maybe there was life there. There's definitely indications that there was water there, and that is a very good indication of life. Okay, last but not least, Venus, where you wouldn't expect any life to be. And this poor robot that we sent up there didn't survive very long. Very sad. And you wouldn't expect life to exist on Venus at all. Venus is really hot. It's full of sulfur. It's going to burn you as soon as you touch it. This rover that had survived already, leaving Earth, right, and then was all the way to Venus and landed, lasted something like 5 or 6 hours, I think. Like, not even. It just melted. So we humans or any kind of life, unlikely. But then this very wonderful woman on the top right, Jane, found what we know to be phosphine gas in the cloud decks of Venus. So these are the kind of atmospheric layers of Venus, right? And this is heavily contested, right? There are lots of arguments to and fro about what this looks like. I am biased because I worked at one of the telescopes that was part of this discovery, and I heard about it before the embargo, and I was super excited. But we have this back and forth about it now, and that's important because extraordinary discoveries require extraordinary evidence. And the importance and excitement around phosphine gas is that it's only produced aerobically. So it's only produced by respiration, implying that there has to be some kind of life there, whether it's bacterial or tiny or otherwise. And at this point, I think we're just sending a mission. You can see this bottom paper here was like, you know what, let's just send something to have a look. This is what I like to call science Twitter. It's just Archive, which is a website where we post our science and argue with each other. It's also free to post science to there, so some of it's better than others. Be mindful. It's not peer reviewed necessarily. But let's say that there may have been life on Venus, and that tells us that 100% of the planets that we've sent rovers to potentially have life. And that may not be a statistically solid argument, but I will take it. And when we think about it on a bigger scale, we have about 100 billion or 200 billion stars in our galaxy alone. And each of those stars statistically has at least one planet. So if planets are that common, it's somewhat naive to think that there wouldn't be life. And we can go into this. This is a big conversation, right? This is more than just a statistical conversation. You can go into the Drake equation. You can go into all the different parameters around what life looks like. But in my opinion, and I don't know, maybe in Liv's as well, maybe we can get into that, life is probably there. So,
well,
Liv, you want to do this
one? Yeah, so if you think about it, we are one planet in a solar system orbiting one star. Like Jess said, we have about 100 billion stars just within our own galaxy. And if you move a little bit further outside of that, we have about 100 billion galaxies in the universe. So that is so many opportunities for life to exist. It would be egotistical to think that life couldn't exist or doesn't, and statistically impossible.
Right. And I just realized we don't have that long, Liv. We've been talking longer than we usually do. How long do we have?
17 minutes and 58 seconds.
Oh, that's actually okay. Carry on.
Right. So we are in a particularly awesome time for learning about the universe, because prior to 2015, when we had the very first gravitational wave detection, everything we knew about the universe was because of light. And while we now have four what we call multi-messengers, we have the EM&M spectrum, cosmic rays, gravitational waves, and neutrinos. E&M, or electromagnetic radiation light, is still an amazing thing to have to learn about celestial bodies.
Oh, you want me to go?
Yeah.
I would like to let everyone know that's the first time we've remembered all four multi-messengers in the 6 or 7 times we've done this talk.
And I don't have notes in front of me. So a lot of what I do is spectra, or spectroscopy. And so we have 3 different kinds of spectra, right? A continuous spectrum is something like a light bulb. So if you were to take a diffraction grating and look at a light bulb, you would get this beautiful continuous rainbow. Nothing would be missing. It's just light in its purest form. One of the questions we like to ask is if stars, which stars are also continuous spectrum, our own sun is a continuous spectrum, why exactly, when we look at it, do we not see a continuous spectra like this? And the answer is because the atmosphere around the sun, because stars also have atmospheres. I remembered, Rika. And when we look through them, we're seeing what the cloud is taking away from the light. So when you're looking through a cloud, you see something like an absorption spectrum, which is the bottom. Those black lines that are missing are what the cloud is taking away, or what the cloud wants. And, in terms of electrons, they all want to be happy and stable and grounded, as do we all. And so even when they're excited and in their upper levels, they're still going to try and get back down to the ground level as quickly and efficiently as possible. And when they do that, they kind of spit out different energies of light. And depending on which level they're at. So when they do that, you get the emission spectrum, which is the middle one. Each one of those is a wavelength of energy that's being emitted by that particular light. And ooh, got distracted for a second. Sorry, there's the ADHD going. Um, so we have these three different ones. And the coolest thing about the emission spectrum is every single element that exists in the universe has a very specific and unique light fingerprint. None of them are the same. So this one here is for hydrogen. And if you see exactly this map on any given spectrum, like reader, right? It's going to say this is hydrogen. It can't be anything else. And so when we look out at the stars or at the universe or galaxies, and we read their light, we can tell exactly what's inside them based off of their light signatures, based off of this fingerprint.
Nice. Next slide is what I'm being told. I love this one.
Yeah, so I mean, when we're looking, we have the visible spectrum, and that's what we can see with our eyes. But we have all of these other telescopes, all these other methods of looking at light that we can't see with our eyes. And different things are going to emit different frequencies. They're going to emit different wavelengths. Stuff that has super high frequency has the bluer end of the spectrum, more energy. Those are going to be your black holes, and stuff that has, longer wavelengths, are redder end of the spectrum, cooler if you're talking about stars. Those things are going to be small and dim and less energetic. But the hearts here are telescopes that Jess has all worked on.
Yeah, love them. So excited for Roman, guys. That's going to be an incredible telescope. Okay, I just like to push that little bit of space telescope in my life. So that's Chandra. Wait, no, that's UVEX. So the one that's labeled Chandra the second time with the heart, that's not launched yet. That's going to be a UV telescope. Kepler, very famous planet hunting telescope. Roman is going to just blow everyone's minds just straight out of the water. And then SMA is the submillimeter array on the summit of Mauna Kea. Okay. Did you want to talk about this, Liv?
Oh, yeah. Okay, so I mentioned briefly about the light and energies. So when we're talking about stars, things that are really, really big are going to be very, very blue. The bigger the star, the shorter the lifespan, the more energetic it is, and it's going to be on that bluer end of the spectrum, the purpley side, right? As you go through them, you can see that they get smaller, they get dimmer. So our sun is kind of right in the middle, very average size, very average color. Um, you get to be, I guess the surface temperature is about 5,500 Kelvin, something like that. But as you go towards the smaller end of the stars or the main sequence, you're going to get smaller stars, redder in color, and they're going to live for a really, really long time. Our red stars that we have now, their end date, the amount of time that they will live, exceeds the current age of the universe. So none of them have actually died yet that we could see, right? Unless they were destroyed by some other thing or eaten by some other thing. But yeah, live bright, die quickly. Small, small, red, awesome. And this is going to be relevant when we talk about the next thing that just really, really loved.
The Zoom keeps saying I'm doing a thumbs up. I wasn't, but I am for you, Liv, always. Okay, so
Loving my awkwardness right now.
Liv has given you some really, yeah. Liv just gave you some great actual schooling in physics. I'm going to go back now to the skeptical nature of Star Trek in our timeline. As of the time I made this figure, which was 6 to 8 months ago now, there were 5,747 confirmed exoplanets. So these are planets outside of our solar system hold on, I'm going to move on because it's making my video slow. Okay, so there are that many planets that are called exoplanets. These are planets which are not orbiting around our sun. They are orbiting around other stars. So their systems can look like ours. They can also look nothing like ours. But and if you come to our talk later, you'll hear about some Jupiters that are crazy. Not crazy. That's ableist. Wild. So that many exoplanets, again, unlikely that there's not aliens. And the one I showed is actually an artist's representation of my favorite exoplanet, Kepler 22b, which gets wrong. A lot of media gets Kepler 22b wrong. It makes me very upset. A lot. It's an ocean planet, right? 90% water. Stop like making it look like a desert planet. It's not. That's the opposite. Heat and dryness is the opposite of wetness. For a very basic science lesson. Okay, so let's talk about Vulcans. Vulcans are my favorite. I identify definitely as a Spock in this lifetime. The reason we're going to talk about Vulcans is because Vulcans are the first aliens to make contact with us in the Star Trek timeline. And in fact, Contact Day is coming up, 4th of April. And we don't have that long, until they are going to come over and say hi. So we need to get our bums in gear to create a warp drive by then. But where would they come from? And what would their planet be like? Does their planet exist? The picture on the left here shows Vulcan's namesake, which was a theorized planet back in 1846. I think it was used to explain the retrograde behavior of Mercury, which we now know is just about orbital motion and how things are perceived. But it was kind of theorized as being this 10th planet. I mean, I don't know how many they knew at the time, but this planet that was inside the orbit of Mercury, and it was called Vulcan. So that's it. I beg your pardon?
2063, April 5th, 2063 is when.
April 5th, 2063. Sorry. Why did I think April 4th? Doesn't matter. We haven't got that long, is my point. So, first of all, we want to think about the Vulcans as a species. They are essentially humanoid, right? They look a lot like us, but they have these kind of superpowers. They're very smart. They're very logical. I think that's a superpower in my mind. But the physical characteristics that they have that aren't built from cultural perspective, things like really good hearing, really good sight, these are all consequences of evolution. And that will have been a significant factor when we think about what their planet would look like. So the star, which is often cited as being the star that Vulcan orbits, is a real star. It's called 40 Eri, or 40 Eridani. So this star is about 16.5 light years away from Earth, which means that moving at the speed of light, it would take us 16.5 years to get there. So obviously it's quicker with warp speed, but I still warp speed maths is yeah, the way we travel to and from Vulcan a bit quick, but whatever, it's fine. So yeah, it would take 16.5 years to get there. Could it support a Vulcan? Could it support an Earth-like planet? A lot of that has to do with what kind of star you're orbiting. Because if you're orbiting a star with lots of flares, or if you're orbiting a star that's too big or too small, you're not going to get the right amount of light, the right amount of heat to sustain your world. So let's talk a bit about 40 Eri. It is a K-dwarf. That means it is slightly smaller and cooler than our sun. Our sun is a G-dwarf. Dwarfs being the main kind of the main life part of a star. It's the part where the star is burning hydrogen. So K-dwarf burning hydrogen is what I call a trinary. This isn't a real word. They don't allow it in the literature, but this is a star where there's 3 of them, so a binary is 2, a trinary is 3. And this picture on the left is actually a picture that was taken by an amateur astronomer, which is awesome. So much of the work of astronomy is done by amateur astronomers because there is just so much out there. Citizen science is a very, very useful endeavor. Please do it for us so that we can find more discoveries. So the A here is 40 Eridani. B and C are the secondary and tertiary stars. One is a red dwarf, which means it's very cold. Those ones that Liv was talking about earlier that we haven't seen die yet. One of them is a white dwarf, which is a star that has gone through its entire life and is dying slowly, just kind of fizzling out. Neither of these stars are going to impact our planet. Sometimes they would. In this case, it won't. But they are there. But does it have a planet, right? We're not going to be living over there on stars. Does Vulcan exist?
Wait, before we get there.
Yes, go for it, Liv.
Go back one for just a second. So K-Dwarf, when I mentioned the size and color of stars, K-Dwarf would be very dim, very small, very red. But one of the things we like to talk about when we have done this in the past is that our sun is a particular size, but does anybody have any idea what color or what color our sun peaks in? Like what color of the spectrum does our sun peak in? And for time's sake, I'm just going to tell you that it's green. And that's great, right? So, but think about it in a little bit of a different way. The reason that our plants on the earth are green is because that is what our sun peaks in. So because our plants want to be able to absorb as much possible light as they can. That's how they continue to live, right? So our plants are green because our sun peaks in green. So when you talk about this K-Dwarf and possible Vulcan, one of the things that I love about Star Trek is their attention to detail. And if you think about what color the plants on Vulcan are, you will remember that it is not green, but red, because their sun peaks in the red. And that's amazing.
I love that. I know that's your favorite tidbit, and I love it. Okay, next. So does Vulcan exist? Does the planet Vulcan exist? The answer is maybe. Here we are back in academic Twitter. Not actual academic Twitter. We don't go there anymore. This is back to archive is what I meant. And the answer is maybe. So there is a bias here, right? Astronomers like Star Trek, they want a planet to exist that could be Vulcan. But actually, there is some evidence that it might. And this is a bunch of different observations of what's called the radial velocity. So this is how a star is impacted by things that orbit the star. So when our Earth is obviously held in gravitational motion around the sun, but the sun will also wobble a little bit. Everything is always in motion. So we can record those things and say, okay, there's this kind of planet of this size around this star. And like I said, it's been going back and forth a bit. But we're, there could be one there, and it would be, for where it sits, we think rocky, which is not, as in not gassy like Jupiter. So let's say there is, for the sake of argument. It also has to be in the right place. There's a lot of factors here that have to fall into place for this to work. So let's say there is a rocky or terrestrial, quote unquote, planet, whoa, my laptop, around 40 Eri. Where does it have to be? Now, you want your planet to be able to sustain water, as we explained a while ago with Mars. And in order for a planet to sustain water, it has to be in what we call the habitable zone, or the Goldilocks zone. So this is the distance from your host star or your sun where liquid water can exist without boiling off or freezing. So if you're too close to the sun, your liquid water is going to boil off. If you're too far away from the sun, past what we call the snow line, all your water is going to be in the form of ice. No, neither of those are any good, no good. You want your water to be water. So we know Earth's water is water. In fact, it's raining outside right now. I can hear it. It's very distracting. The rain. There's my brain going. So we therefore know that our Earth is in the habitable zone of our sun. And that is at exactly 1 AU, or astronomical unit. Now, this is not a perfect system that was created. This is what we have labeled it. So we have labeled that distance as being 1. Astronomers like things to be 1. It makes math a lot easier. So a lot of measurements on this scale, on the scale of a solar system or a star system, are done in what's called AU. So Jupiter, for example, is 6 AU away from the sun, which means it's 5 times further away than the Earth is.
But 1 AU is equal to 93 million miles.
One
And
AU is
basically,
93 billion miles. Thank you,
because
Liv.
that's where we're measuring from where we are. So we're just going to start from us, right? So us to the sun is,
Or
we're going to keep doing that.
1.5 times 10 to the 11 kilometers if you don't use freedom units like Liv does. Okay. Go. Oh, this was just more about the habitable zone. Liv, do you want to say about red giants quick?
Um, yeah, just that when our sun actually dies, it will not be some like catastrophic explosion. It will just kind of get bigger. And as it gets bigger and redder and goes through its red giant phase, it will like extend further out than it is now. So the second image here is by the time, it gets to where it needs to go in its red giant phase, it will kind of consume, or at least the atmosphere will consume Earth and Mars and all of the inner planets. And it will just be far, far too hot to live there. But in that sense, Jupiter and Saturn will then be in the Goldilocks zone. Wouldn't really help because there's no actual ground on those planets, but
You could live on one of the moons.
yeah, you could live on one of the
I think
moons.
it's a bit okay. I will clarify here. I think it's a bit unfair to say a red giant is the start of the end for a star. It's actually their helium burning phase. It's the stars I work on. I feel personally vilified. That is
I'm
just the
so
next
very
phase.
sorry.
That is just the next phase. All right. You get your main sequence, your subgiant, your red giant, your horizontal branch, your red clump, your AGB. Then you start dying. All right. Stuff in between.
Jess
She's
is
gonna
a galactic archaeologist, which I don't think she actually said, but that just means she
I
studied
did.
stars. Did you? I don't remember. Anyway,
Yeah.
she didn't. That's
I
what
did
she
at the
did.
beginning.
She's basically the Evelyn
Okay.
O'Connell of space.
I was thinking about this the other day. It's Evelyn Carnahan, technically, isn't it? Because I'm not married to Rick. Whatever. So, does Vulcan fall within the habitable zone of 40 Eri? The habitable zone of 40 Eri would be closer to the star because, as we said, it's cooler. It would have to be closer for the water to be liquid. And that would be at 0.6 AU, which is 60% of the Earth's habitable zone. Does our theoretical planet, if we do the math, does it fall into the habitable zone? Yes, it does. It falls in there almost perfectly. So if Vulcan does exist, it exists within the habitable zone, is what we know. So that's awesome. I'm going to say Vulcan, definitely there. Can't wait. All right. But there are a few other things that have to be taken into account before we consider our planet habitable. And this is kind of the next stage in what we think about when we think about the habitability of a planet. Water is a very important one, of course, but there are three other very clear distinctions that have to be made. The first is the planet has to have a magnetic field. The second is the planet has to have tectonic plates. And the third is a planet has to have an atmosphere. And all these things work in tandem to create a sustainable and habitable world. So I'll talk about each of these a little bit because new discoveries are being made and they're really exciting. So the first one is the magnetic field. This is a Hubble observation. So despite the fact that we've got a new Hubble with a JWST, Hubble is still doing incredible work. Hubble is just a incredible instrument. It's insane that it works this well for this long. This image here, this bit of data here, is the first ever image of the atmosphere, the magnetic field of another planet. So this isn't the actual picture of magnetic field. Obviously, we can't see them with our eyes, but it's showing the effect of the magnetic field as the wind from the star that the planet is orbiting around is blowing against it, right? So you can see the particles in what's called a magnetotrail being swept off the surface of this planet. This is for HAP-P11b, a known exoplanet. And the magnetic field is vital for retaining a stable atmosphere. And what do we need an atmosphere for? So an atmosphere, necessary for breathing, of course, and necessary for retaining the temperature and a lot of other really useful things that we need on our planet in order to live. And what's really cool about atmospheres now is we're starting to be able to observe them. So like I just said, we're now kind of able to observe magnetic fields, and we're now also starting to observe atmospheres of planets which are not in our solar system, which is very cool. So this is the James Webb Space Telescope on the right. This is the atmospheric composition of WASP-39b, which is an exoplanet. This looks like, sorry, what was that, Liv?
Ghibli Wibbly Space Telescope.
Yes, the Ghibli Wobbly Space Telescope. I shouldn't have said James Webb. We don't use his name because he's problematic. So Ghibli Wobbly Space Telescope, or JWST, take your pick. The plot here on the left shows what is in the atmosphere of that planet. And the way we do that is through a method called transmission spectroscopy. So when the planet moves in front of the star and we can see that happening, we point our telescope very, very directly through the atmosphere of the exoplanet toward the star. So as the light is traveling through that atmosphere towards our telescope, it's picking up on the things that are in the atmosphere. So just like Liv was saying before with our absorption and our emission spectrum, we can then calculate what exists within the planet's atmosphere. And we can find from that that WASP-39b has water, it has carbon monoxide, it has sulfur dioxide, it has a bunch of really cool things in its atmosphere that actually are quite conducive to life, although it doesn't, as far as I know, doesn't have things like phosphine, which you would expect to see if there was aerobic life, or methane. But I don't know. I'm not a astrobiology person. That is Ashley, who spoke earlier today. Maybe she said a bit about that. Okay, so the final one is plate tectonics, and this is some of my work. This one is actually eventually going to be released soon. I need to update this because I know this is a bit intense, this plot, but I'll say this. To have plate tectonics exist on a planet, which to say is volcanoes or any kind of movement of the what's called the mantle of the planet, which is the bit that we live, sorry, not the mantle, the, wow. Help me out, Liv. What's the bit we live on?
Oh, the crust.
The crust. Thank you. The crust of the planet. The crust is always moving. It's moving under. It's creating earthquakes and volcanoes. Things are annoying to us right now, but are vital for creating life, for stirring up the mantle, for moving around the compositional materials for life. And in order to create plate tectonics that are gonna do this slippy, slidey, crusty thing, you have to have the perfect, well, not really perfect, but you have to have a good ratio of magnesium to silicon. So these are two elements that we know are very similar between the sun and the star. So, sorry, the sun and the planets that orbit it, because the planets that orbit a star are just made up of the same stuff the star is made up of. So we can measure how much silicon and magnesium are in a star and assume that the planets around it have roughly the same amount. Then we create a ratio, the magnesium to silicon ratio, which is how much magnesium there is on the top and how much silicon there is on the bottom. So if this number is bigger than 1, there's more magnesium than silicon. If this number is less than 1, there's more silicon than magnesium. And in order to create plate tectonics, you want more magnesium. And that is all about mineralogy. I'm not going to get into it. Just know that you need more magnesium. So in my work here, we took the magnesium to silicon ratio for a whole bunch of stars, for about 7,000 stars. And these stars don't necessarily have planets, but we're kind of inferring that they might. We have the ages of those stars along the bottom. And in this case, we know that a star that was born 14 billion years ago was born at the beginning of formation, and therefore has kind of represents the composition of the galaxy at the beginning. And a star that was born recently will represent the composition of the galaxy now. And all you need to know is look at that trend going downwards. The magnesium to silicon ratio is lessening, which means that at some point, if you extrapolate this line is at about 10 billion years, we will no longer be able to make habitable planets in our galaxy because we will no longer be able to make plate tectonics. And I'll be very clear about this because it's always asked. Obviously, this is not the only metric for habitability, but we're getting there and we need to think about it. So that's plate tectonics. And with that, I think, oh, we have the one more slide. These are my candidates for Vulcan. These are the planets I think could be Vulcan. And obviously they're going to come and save us from this madness. Please, if you're out there. Sorry, what was that, Liv?
So hopeful.
Yeah, so hopeful. So I hope we've answered these 3 questions today. And I hope you guys all think that we're on the timeline, because I certainly do, and I certainly hope so. Although obviously that means we're going to have to do another war, which isn't ideal. But the 3 questions: why haven't aliens contacted us? Because we're not ready. Are there aliens? Yeah, probably. Is Vulcan a real thing? Maybe. That's probably where they are. I hope you've got some clarity on those things and learned a bit of science along the way. Before we leave you, we just want to point out our nonprofit. Our nonprofit is called the Neuroverse Initiative. I'm the CEO, Liv is our CFO, and all the science that you see this weekend has come from our collaboration, from our scientists who work with us. So Liv and I are both neurodivergent. I have autism and ADHD, and a lot of space scientists also are. So we work at the intersection of space science and neurodivergence, where we try and support space scientists to thrive, basically, to achieve their goals, whether that's in academia, in engineering, in rocket science, in school. And the reason we're here today is part of our advocacy arm of the nonprofit that goes to non-traditional, kind of locations, like Star Trek conventions, and brings science communication from neurodivergent scientists. So we really hope you've enjoyed today. If you're interested in donating to us or finding out more about us, that QR code can take you there. I'm sure Ryan can put our link on the site if it's not already there. And I'm always happy for people to reach out to me, although I have stopped giving out my phone number, Liv.
Thank you for that. Also,
Liv does my legal things. I am chaos.
Just a little bit more about our Neuroverse initiative is that, yes, we work at the intersection of space science and neurodiversity, but one of the coolest things about our board is that every single one of us is neurodivergent. So Jess is ADHD, I am also ADHD, and our board is not just astronomers or astrophysicists. We also have physicists and psychologists, and we just really like doing stuff to help other people in the sciences, which, is why we're here. But also, in terms of partners, Startorialist is one of the coolest, and they have...
Oh, I'm wearing a Startorialist necklace right now. It's the speed of light.
Nice. Cool. But if you go to their site, we have a discount code. If you click the button, just...
Oh, that's the deep field. I don't know why that's on there. Maybe we didn't. Okay, I think maybe it's
oh, it's on the other one. Okay, anyway, it's I'll put it in the chat. But if you go to their website, they have really cool stuff. Like if you have kids, they have books like this. Or if you look back there, you'll see planets. Those are celestial buddies. They have those too. And also clothing. That's all space accurate clothing, and jewelry, and really anything that you could think of. This necklace, right? It's my moon necklace. It also says make space for everybody, but things like that. So do that. And we have about 5 minutes. So if you want to ask us any questions, I have the chat open and I can read them. Ryan says we have about 13 minutes.
You want to come back, Ryan? You want to chat to us? Ryan's lost his voice. Should I plug that? I love this mug so much. This is my second Anson Mount mug. Love it. He makes amazing mugs, guys. If you find him at conventions, he sells them and they're incredible. Yeah. And they make your coffee taste better. This is my second one. Look, it even has a little thumb bit. So good.
We will be at Las Vegas in August.
Someone asking?
So, yeah, we'll see you, TJ.
Whoop, whoop. I hope we'll have lots more science at Vegas. Ryan can't speak. He's lost his voice, so he can't vouch for us. So I'm just going to say, yeah, of course, there's going to be a whole ton of us. We're going to do lots of science. It's going to be really, really fun. We'll be causing trouble, making havoc, or I make havoc. Liv sorts out things.
I also make a little bit of chaos.
You do make a little bit of havoc. We do chaos, yeah.
Mild chaos.
Mild chaos.
If you have necklaces, maybe a boronite one. That'd be cool. Or
we need to tell Emily that.
Yeah.
We need to tell Emily that. I do. So I do know that one of our board members wants to do some partnership to do neurodivergent specific merch, and has some amazing designs. So you might see that appear on our site soon. Although I don't know what that looks like. Oh, these two, yes. So one of a lovely guy we met at one of the cons this year. 3D prints these badges. You can find, when you find him at a con, you will find the badges, and he's also making us some neurodivergent ones, which I love. And
we do wreak havoc everywhere we go, especially conventions. I'm assuming that's from Ryan. Ooh.
I can't see this, so you're just laughing at things I can't see.
Ryan needs a reverse ventriloquist dummy to speak for him.
Poor Ryan. He is quite sick. Quite funny. Not that he's sick, that he sounds.
No space questions, guys? Or,
Autism questions or
autism,
you're pinned, Liv.
burning astronomy questions not related to anything we talked about, or,
Star Trek questions.
Star Trek questions. Do you have any programs that are aimed at kindergarten-aged kids? Currently,
So,
go ahead.
okay, so I realized you're pinned, Liv. I'm going to remove your pin so we're side by side. Yeah. So we specialize in the area kind of after high school. So we're looking at adults. Although we do, our science outreach does touch all age groups. The reason for this is that there are actually already many, many, many programs that help children. There was not enough by any stretch of the imagination, but the area that we focus on really has no supports. Once children leave high school, often the supports leave with them. People tend to think that autistic children don't become autistic adults, which is, wild. Having said that, if you fill in the contact form on our website, I do know a bunch of places where you can access those kinds of services. We, and I probably legally have to say this, are not in the clinical space. We are not in the medical space. We do not diagnose, but we do kind of accept self-identification and things like that. So if you reach out to us, we can always kind of try and point you in the right direction. I'm also the communication and programs manager for a research innovation center called the Friss Center for Autism and Innovation, which is housed in the School of Engineering at Vanderbilt University. They're a partner with us at the nonprofit, and we also do a lot of work in what we would consider the neurodiversity work space or neurodivergence at workspace, which is a very growing community. So yeah, please always feel free to reach out to us. If we don't have what you need, we can point you in the right direction.
And we also have on our website resources, a resources page, a message board if you want to join our community of people. We're going to start posting like once a month questions for community members to just kind of talk to each other and, share experiences, stuff like that, kind of build the community around it and us. Question.
This is all growing right now as well, so please keep in contact with us. We have social media and things as well, which I don't touch, so Mike does it and he does an excellent job.
A question.
And we'll continue to grow once we graduate.
Yeah.
Go for it.
What do you think the impact quantum computing and AI might have on our ability to reach FTL speeds?
Yeah. I have so many feelings about it. So AI, in my opinion, is a big blessing and a big curse, right? It can really impact the way that we, especially in astronomy and engineering, inform our models and understanding of how to build, right? How to build, what to build, how to improve what we have. But the impact of AI, and this kind of weirdly enough goes back to the Kardashev scale, right? Is that it takes a lot of energy, it costs a lot of money, it's can be used in nefarious ways, it can be used in malicious ways, which I think is probably the general public's biggest concern around it. I know people often think about, oh, well, what if AI becomes sentient and da-da-da-da. We don't have to worry about that right now. I think the bigger problem is malicious use. And all these things, quantum computing definitely will push the frontier, and we're not far away from that being a day-to-day thing. I'm not a physicist though, so I'm an astrophysicist, but so I don't think about quantum all that much. It's very confusing. But my understanding is
we'll have a physicist with us in Vegas, so he might
we will have an actual physicist. He does CERN stuff as well. Mike talks about what he does, and I'm like, what? There's like quarks and like gluons, and there's up quarks and down quarks, and it's very weird.
Yeah.
Things spin, but they don't though. Yeah. You'll have to ask him about that. But yeah. I mean, yes, all these frontiers of technology that we reach, and quantum and AI are both big markers in that, do spur our discoveries. But at the end of the day, what we need is both funding and people who are able to make those discoveries. And there's concern about that right now for various reasons.
Yes, we do need more humans to become sentient. Question: how do tectonic plates form in the first place?
Was that a comment you read, or did you say that?
It is a comment.
We do. Oh my word. So we're not allowed to say that though, because we're a nonprofit. Our opinion. So what's
and the
the
other thing
plate
about
tectonics? Okay. So
tectonic plates, we're asterisking this with we are astrophysicists, not geologists.
yeah. So what I know about this is because I wrote the paper with the magnesium and silicon, but galactic archaeology, my area, is very interdisciplinary. We do lean on a lot of science, other types of science, which is generally what a lot of sciences are starting to move into now. It used to be that you could be one person in a room with a bunch of books, but now we have these big collaborations with all kinds of scientists helping out. And so for plate tectonics, essentially you've got your iron core, right? Your core of your planet where all the heavy metals sink. Then you've got your mantle, which is your I think of it as lava, right? Think of it as the stuff that comes out. I actually live about 5 miles away from Kilauea, which is erupting right now. You should definitely all go to the YouTube for USGS and check out Kilauea's eruption. I went the other night. It looks amazing. That's what our mantle is essentially made of. And the top layer is a hardened crust, right? So plate tectonics happens because when you have more magnesium to silicon and minerals form from that, the minerals that form from a magnesium dominant mantle are different to the ones that form from a silicon dominant mantle. And the ones that form from the magnesium dominant mantle are more viscous and can break things apart, is my understanding. That's a very, very, very layman's argument of it, right? And once you've started cracking the surface of things start to move around because the mantle's moving, right? It's flowing, it's moving. Ryan says we're running out of time, which is great because I have nothing more to say in the answer to that question other than you need to contact a geologist.
Yeah.
Or I can send you some links. Liv, was there anything else before we go?
Not a like actual question, but a comment of just science being mostly lonely profession. No, 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 no. Oh, didn't realize how many other sciences are involved in astronomy. Well,
Yeah, big time.
everything that you can do on Earth, right, can also be done on another planet.
Yeah. So the people who saw Ashley's talk earlier will have probably heard a bit about this. They have Ryan, you're trying to distract me in the chat with pictures of kittens, man. That's adorable though. I cannot. He wants us to leave. Okay.
Okay,
So
but yeah, we we do have to say goodbye.
it's been a pleasure. We'll be back though, right? In like a few
Yes,
hours.
we will be back at 6 p.m. to talk about Europa and
6 p.m. Eastern or Pacific?
Pacific time.
Okay. So
6 p.m.
4
Pacific.
p.m. for me, right? Yeah. Okay.
And yeah, so we'll see you then. If you have any more questions for us, you can ask us then. We're going to talk some really cool stuff about some moons. And yeah, so thanks for joining and hanging out with us, and we'll see you later.
Bye.